We are back with our summer packet, and today we are going to cover the calculus concepts in this packet. These are calculus concepts that you covered at the end of pre-calculus last year. So we are going to begin with limits. Limits are super important. We hit them at the beginning of the year, and we hit them in the middle of the year, and we hit them at the end of the year. So they're super important. The concept of a limit is behind everything that we do in calculus. So we will keep that in mind when we look at these problems. All right, number one is the limit as x approaches 2 of this function. Now, it's important that you know that a limit as x approaches a number is not necessarily the value of this at that number. That's a technique we can use, but it's not necessarily always true. All right? A limit is the value of y, the value of the function that is approached as x approaches this number. Okay? But our first technique to every limit is indeed just to plug in that number. So that's what we're going to start off with. So I'm just going to plug in this 2 for x. If I do that, I'm going to have 4 minus 6. 4 minus 6 is a negative 2, plus 1, and I get a negative 1. Get a darker color here. Negative 1. And then on the bottom I have a 4. Since that is a number, that's a number, I can keep my equal to sign, and that's just my answer. So the first technique is always just to plug in the number for x. If you get a number, then that is your limit. In number 59 here, if we employ that same technique, just plugging in 2 for x, immediately I see that in this denominator I'm going to have a 0. So I know that I'm not going to be able to use this equal to sign, because it's not going to be equal. Something with a 0 on the bottom is not going to be equal. If I plug 2 into the numerator, I want to see what's on top. If I plug 2 into the numerator, I'm going to have 4 plus 12, that's 16, minus 16 is also 0. So I get 0 over 0. This is a form of an indeterminate. This is indeterminate. Indeterminate. Okay, it's indeterminate form. We have several indeterminate forms. We have 0 over 0, infinity over infinity, negative infinity over infinity, and then we have some more like 1 to the infinity, 0 to the infinity, things like that. We'll hit these kinds later. We'll hit those kinds in the springtime. But for now, we're going to be focusing on those types, okay, what to do with those. So if you get a 0 over 0, that means we need to do something. We need to manipulate this somehow, okay? One thing that we can do to manipulate that is to factor what we can, and hopefully we'll reduce out what made this 0. So if I factor this, I keep my limit, because I haven't taken the limit yet. So I'm factoring the top, and it factors into 8 and 2, plus and minus, like that. And I see that this function has a hole. The graph of this function has a hole when x is 2. There's a hole when x is 2. So that means whatever y is doing, whatever the function is doing, there's a hole there. So the limit will be approaching that value. The limit will be that value. It'll just never reach there because there's a hole. Okay? So these can cancel out. We can put 2 in for what remains, and this will be 10. So this value is y is equal to 10. The limit is 10. Even though the function is not 10 there. It's just approaching 10 there. That's the meaning of a limit. Number 60. Okay, if we put 0 in for x, I immediately see that the bottom is 0. I know that the bottom is going to be 0. The top is going to be the square root of 16 minus 4, which is also 0. So again, we have that indeterminate form. So we have to manipulate this. Another technique that we can use to manipulate is to, in this case, we can't factor the top, right? Instead, I'm going to multiply top and bottom by, whenever I see the square root plus or minus a number, I want to multiply top and bottom by the conjugate. The conjugate of the numerator will be the square root plus 4 over the square root plus 4, like that, okay? So I'm multiplying by 1. It's a clever form of 1. This form of 1 will allow the numerator to look nicer. So I'm going to have, I have not taken the limit yet. So FOIL this out. I'm foiling the top. So the square root times the square root is just what's inside. The middle term here will zero out, which is the entire purpose of multiplying by a conjugate, so that this middle term will zero out. And then we'll have minus 16. Okay? On the bottom, we have that, right? Do not distribute. Do not distribute, because if you distribute, you're going to lose what's about to cancel. Just leave this, 16 plus x plus 4. Just leave it like that. Because now we see up on top here, we just have an x, because the 16s cancel out. So we just have an x. So this x is going to cancel with this x down on the bottom, leaving a 1 up on top and this parentheses on the bottom. And now we can put 0 in for x. So now if we put 0 in for x, we have 1 on top, and on the bottom we have the square root of 16 plus 4, 8. So this limit is 1 over 8, 1/8. Okay? Number 61. This limit is of x as x is going to infinity. X is going to infinity. Now, when x is going to infinity, I treat this very differently. I'm not going to plug in infinity for x. Okay? Infinity is a concept. We can think of it as plugging in a huge, huge number for x. That's fine. So if we plug a huge unbounded number in for x, if we do that, here's my thought process, and this is how I would really like for you to think of it. If we plug a huge number in for x, this plus 2 on the bottom will be insignificant compared to this x cubed. So I can ignore it. I can just ignore it. This plus 1 will be insignificant compared to the x cubed. This negative 3x will be insignificant compared to this x cubed on top. So this behaves like, and I could write this, I think I will write it. This behaves exactly like 5x cubed over 7x cubed. These two limits are the same. Now I see that the x cubes can completely reduce out, leaving 5/7. So that limit is 5/7. You may have learned, when x is going to infinity, you may have learned this as a little rhyme. Top O, bottom no, same co. I don't like rhymes when very simple logic can take its place. Okay, I don't mind rhymes when the logic is hard, but this logic is so easy, and this is the way I would really like for you to think of this. As x goes to infinity, these are insignificant. What's left reduces to 5/7. It's very easy. To me, it's easier than that rhyme, which I always have to think about because some students like the rhyme. So anyway, there's my thoughts on that. Okay, in number 62, we have a one-sided limit. x is approaching 2, but only from the positive side, okay? Only from the positive side. When this is the case, here's how I like to think of it. I like to think of this as plugging in a number very close to 2, but on the positive side of 2. In other words, if this is 2 on the number line, I'm only coming at 2 from the right. This is a right-handed limit. So, in other words, I can put in, for x, I can put in something like that. If I put something like that in for x, I see that I have 1 on top, and I have, on the bottom, I'm going to have a very, very small positive number. A very small positive number. So we have 1 divided by a tiny positive number. And when you're dividing by a very tiny positive number, you're going to get infinity. And it's going to be a positive infinity. Just like that. Okay? That limit is infinity. Sometimes on a multiple choice answer, they will write the answer as infinity, or sometimes they will call that a does not exist, because it's not a number. A does not exist we abbreviate to be DNE. Okay? Kids ask me all the time, do I write infinity or do I write DNE? And here's the difference. What is that shape? What is that shape? Well, we can call that shape several different things. We could call it a square, if I make this if I further reinforce that. Yeah, that is a square. Okay. A square would be the most precise way to call that figure, right? But this is also technically a rectangle. And technically, it's a quadrilateral. I can spell quadrilateral, okay? So the difference between these two, okay, the infinity and the DNE, infinity would be like calling this figure a square. DNE would be like calling this figure a quadrilateral, okay? So they're both correct. They're both technically correct. Infinity is the more precise answer. It's more descriptive of what's happening. Okay? So, there you go. If you have any questions on that, let me know. All right. This is also going, x is also going to infinity, right? So I'm thinking of this, since there's a sign on top, I'm thinking of plugging in a very large unbounded number for x here. Well, on the bottom is going to infinity. It's very large and unbounded, so it's going to infinity. The top, what is that y value going to? Well, sine oscillates. Sine x oscillates between -1 and 1. So up on top, I have some number between -1 and 1. And I'm dividing it by a huge unbounded number. If you divide a number between -1 and 1 by an extremely large unbounded number, you get 0. So that limit is 0. You can confirm that. You could confirm that. If you wanted to see what's happening on that one, we could go and take a look at the graph of that. Sine x divided by x. And I'm going to just zoom for it. Okay, there it is from about 0 to 6-ish, right? But if I change my window to go to, maybe 50, you can see, that as x is going to infinity, we're getting closer and closer and closer to the x-axis, where y is 0. So that limit is 0. Okay? You can see it oscillating, but it is going to 0. Okay? All right. So those are just a few examples of limits. It by no means covers all the limits that we did, that you guys did at the end of pre-cal. But these are just a few. Just get your mind thinking. All right. The next topic is continuity. You need to know the definition of continuity and how to apply it. So a function f is continuous at x equals a if and only if the limit from the left is equal to the limit from the right, and both of those are equal to the function at that value. So up here in number 59, when we had this hole, remember we had that hole? This would not be continuous because we have a hole when x equals 2. This is continuous at x equals 2 because we just got a number there. The limit from the left was equal to the limit from the right, and that's equal to the function value. Nothing funny is going on there. Now, at x equals negative 2, no, that would not be continuous because at x equals negative 2, we are not continuous. We have an asymptote or a hole. Something's going on there. Okay? So limit from the left is equal to the limit from the right, and now those are both equal to the value of the function at that a value. I need to plug in again. Okay? All right. So a way that I might ask you, if you know the concept of continuity, is like this problem, number 64. Find the value or values of k so that f will be continuous at x equals 2 given this piecewise function. Well, I see that alone each of these is continuous. Each of these is continuous if we consider them individually, not in a piecewise function. This is a parabola, this is a line. So parabolas and lines are always continuous. So the only questionable spot is when x is 2, where they change. We want to know, does this function equal this function when x is 2? So when x is 2, kx squared would be 4k. When x is 2, 2x plus 4 would be 4 plus k. We want to know what value of k makes those equal. So we'll have 3k is equal to 4, so k is 4/3. So 4/3, that's what value of k makes f continuous. All right, next we're going to talk about derivatives, okay? And there are some other concepts in here. There's differentiability and things like that, but we're just going to jump right into derivatives here. So know how to find the derivative of a function using the definition of the derivative. Kids like to say, this is the one with the h's. I'm like, yes, this is the one with the h's. So the definition of derivative, let's come over here and state what it is. Definition of derivative of f of x is this. It's the limit as h approaches 0 of f of x plus h minus f of x all divided by h. This comes from, and I'm sure when you learned this at the end of pre-cal, this comes from the slope formula. This comes from y2 minus y1 over x2 minus x1. Okay, and it's where we're going from a point x1, y1 to the point x plus h or x1 plus h to whatever that y value is. Okay? f of x1 plus h. Okay? So that's where it came from. And I know I will develop it in class with you guys, but that's where it comes from. But this is something that we need to know. Okay? And this is something that we will learn at the beginning of the year again, and then you will forget it for a while, and then we'll come back to it again when we're reviewing for the AP exam at the end of the year. Okay? Alrighty, so if our function is this, if that is f of x, then the derivative would be the limit as h approaches 0. I can immediately get rid of these because this is x is approaching 0. So it cannot be those. We don't want x to approach 0. We want h to approach 0. So I already know it's one of these two. All right. So which one is it? Let's see. Here's my function. I need f of x back here in the back. And I see there's f of x here in the back. This is not f of x in the back. They put f of x in the front. And that's going to, that's this switched. So the answer here is definitely A. All right, that's one way that somebody could see if you know the definition of derivative in a multiple choice question. All right, the rest of these problems are just finding derivatives using the power rule, product rule, quotient rule, and chain rule. In number 66 here, I see just a polynomial, so we're going to be using the power rule. So the derivative is equal to add 1 to the power and, sorry, I'm doing the integral. Multiply your power times the coefficient, that will be 12, and then subtract 1 from your power, and that's a 3. So 12x cubed, okay? Alrighty. Multiply your power times the coefficient, subtract 1 from your power. Multiply your power times the coefficient, subtract 1 from your power. And on this one, the derivative of any constant is just 0. The derivative of a constant is 0. So this would be f prime of x. For number 67, we're going to use the power rule, but before we do, I need to do something with this. I'm going to rewrite this as x to the 3 over 4. Remember, the root is in the bottom of the exponent if you have a root. So this is the fourth root, so 3 over 4, the power over the root, plus 7x. Now we can take the derivative. You can call the derivative dy dx or y prime. Either one. They mean the same thing. So y prime or dy dx. You do not need to say both, but I'm using both. Power times the coefficient. Subtract 1 from your power. 3/4 minus 1 is a negative 1/4. Plus, this exponent is a 1. Power times your coefficient is 7. Subtract 1 from your power, and you get x to the 0, which is just 1. So the derivative of 7x is just 7. This would be a safe stop spot. As a multiple choice answer, they may move this x to be in the denominator and make that 3 over 4 times the fourth root of x plus 7. They may do that, or they may just leave it like that. Okay? Check both. But this would be a safe stop spot for us. We are fine with negative and fractional exponents. Okay. In number 68, h is equal to secant x. We want the derivative. So we need to know, you've got to know all of your trig derivatives. So trig derivatives. Okay, the first derivative, the derivative of sine. The derivative of sine is cosine. Need you to know that one. The derivative of cosine is negative sine. The derivative of tangent, is secant squared. The derivative of secant is secant tangent. Okay, the derivative of cotangent. The derivative of cotangent, I think of the derivative of tangent is secant squared, so the derivative of cotangent will be a negative cosecant squared. Got to know that. And then the derivative of cosecant, I think of the derivative of secant as secant tangent, so the derivative of cosecant is negative cosecant cotangent, squeezing that in. Okay? So these are things you need to know. Okay? So, the derivative of secant is secant tangent. Alrighty? Number 69. I see a product of two functions here, so I need to use the product rule. So I start with the first function and take the derivative. The derivative of the first function is 2x. I'm going to call this f prime. Okay. The derivative of the first function is 2x. Keep your second function the same. Plus. Now we're going to keep the first one the same, the x squared, and multiply by the derivative of sine. Derivative of sine is cosine. This is the derivative of that product. Product rule. Okay. For number 70, I see a quotient. So I'm going to use the quotient rule. Here's the quotient rule. Start on top, take the derivative. Derivative of that is 1. Okay, I think I'll just write 1. Multiply by the bottom left alone. Okay. In the quotient rule, we have a minus instead of a plus. Now we're going to leave the top alone and multiply by the derivative of the bottom. The derivative of the bottom is a negative sine x. And now we are in the quotient rule, we get a quotient. The quotient rule yields a quotient, all right? So we get, in the bottom, we're going to have the denominator, whatever the denominator is, squared. Like that. This would be a safe stop spot, written as a multiple choice answer. It would look like that. Okay? All right, number 71. In number 71, I see this 3x here. So that 3x is going to make us use the chain rule. Here's how the chain rule is. Treat this like a single variable, like u. Treat it like a u. But then we need to multiply by u prime at the end. So, f prime of x will be the derivative of tangent is secant squared. So secant squared, keep your argument, and then multiply by the derivative of your argument, 3. So this would be 3 secant squared of 3x. Number 72. Again, I see another chain rule because the argument of my trig function is not just an x. If the argument is not just an x, you need to use the chain rule on it. So y prime or dy dx will be, okay, first find your derivative of 4 sine of x or 4 sine of u? Well, the derivative of sine is cosine. So I'll get 4 cosine. Keep your argument. Keep it. The argument will never change. Now we're multiplying by the derivative of the inside. So the derivative of your argument. Well, the derivative of our argument is 9x squared. So this would be 36x squared cosine of 3x cubed. Okay? Number 73. Well, this is a mess because we don't just have an x here, and we have a cube on our cosine. So here's how I like to tell kids to think about this. Think about this as 5 times cosine of 4x all cubed, which is what this means. Cosine cubed means cosine cubed. Okay, now I'm going to start off with the chain rule where I multiply, or I'm sorry, the power rule. This is just the power rule. So 3 times our coefficient, so g prime will be 15. Reduce your power by 1. When you reduce your power by 1, you're keeping what's inside the same, right? When we use the power rule here, we didn't change x stayed the same, right? So when you reduce your power by 1, keep your inside the same. Now we're multiplying by the derivative of the inside. Chain rule time. So the derivative of the inside is negative sine, keep your argument, times the derivative of your argument, 4. So this becomes 4 times 15. I have a negative. I'm going to pull out the negative to the front. Cosine squared of 4x times sine of 4x. Notice that every time our argument is the same. We started with a cosine of 4x, and every argument of a trig function is 4x. Here we started with 3x cubed as our argument, and our answer had a 3x cubed as the argument. Same thing over here. Tangent of 3x, secant squared, 3x. The argument will always stay the same. Don't change your argument in these. Okay, and one final one. I need to begin by rewriting this as 4x cubed plus 3x all to the 1/3 power. Now I can come in and take the derivative using the power rule and then the chain rule. So power rule first, so 1/3, keep your middle the same, keep your inside the same, subtract 1 from your power. 1/3 minus 1 is a negative 2/3. Now we come in and multiply by the derivative of the inside. So the derivative of the inside is 12x squared plus 3. Written as a multiple choice answer, they would keep the 12x squared plus 3 on top, bring this to the bottom probably, and just call that 4x cubed plus 3x to the positive 2/3 power. And I do see that I can reduce the 3. If I factor a 3 out of the top, I can reduce with this 3 on the bottom. So they probably would do that since it reduces it. So that would leave a 4x squared plus 1 on top. I'm not going to be able to fit it in there, so I'm not going to try. But it would leave a 4x squared plus 1 on top, and this 3 would be gone on the bottom. Okay, so there is some of the derivatives that you guys learned at the end of the year. Derivatives are super important for us. So that's it for the summer packet. If you have questions, email me. we will have a Remind account that you can text me on, and I look forward to seeing you when school begins in August.